The Civil Engineering Laboratory, CEL, has developed kits which can be installed on conventional motor graders and tractors having tilt blades to provide automatic control of blade elevation and tilt. The most recent of these is an experimental kit for the Case 450 bulldozer. In March 1976, a comparative evaluation of the Case 450 kit was conducted on this site. The primary purpose was to compare the construction of a typical earthwork project using present naval construction force procedures and equipment versus the Case 450 tractor with and without the CEL kit. First, 3 100 by 100 foot square plain areas are laid out at the site. Each area is to be sloped with a positive 1.41% grade from the southwest to the northeast corners. For each pad, a benchmark is established for vertical control, and offsets are staked for horizontal control. All construction planning and equipment operations are performed by instructors from the Naval Construction Training Center, Port Hueneme. The overall layout as planned is shown in this artist's sketch. Pad 1 will be graded using a conventional motor grader. On Pad 2, the Case 450 bulldozer without automatic controls will be used instead of the motor grader. Pad 3 will be graded by the same Case 450 bulldozer, but with the CEL-developed automatic blade control kit. Also, the elevation reference part of the kit will be used for all elevation surveying on the pad. This is Pad 1. Standard table of allowance equipment is used for delivery of the fill, for wetting down, and for rolling each pad. The fill is hauled by scrapers. A Galleon Model 118T motor grader levels the fill, and a self-propelled sheep's foot roller compacts the fill. One equipment operator alternates between the grader and the roller. Now the fill for Pad 1 is approaching the required grade. A full day is needed to position the remaining scraper loads and bring the fill sufficiently close to grade for blue top staking. A total of 519 cubic yards of fill is deposited on Pad 1. As the blue top survey begins, the grader and its operator are on standby, unable to work on the pad during this operation. Again, conventional survey methods are used by the surveyors. Because the fill at this point is above the specified grade, all the blue top hubs must be set below the existing surface. The grader operator is a concerned observer as the survey proceeds. It required 4 hours and 7 minutes to complete this task. As the final blue top grading gets underway, the operator proceeds at a considerably slower pace. An additional equipment operator accompanies the grader on each pass. His job is to advise the grader operator and mark the position of the hubs as the grader passes over them. Blue top grading takes all the skill and concentration the operator possesses. Now he's working to tolerances of fractions of an inch, and even very experienced operators can make minor slips. Since the hubs, which are the operator's only reference to the finished grade, are below the surface, he must stop his machine at frequent intervals so that they can be located and uncovered again. The ground man indicates the position of the hub by laying down a stake. This is the most time-consuming and meticulous phase of the grading operation. It is standard procedure in earthwork projects of this kind, where materials such as asphalt or concrete are to be applied to the surface. This operation continues until the entire pad has been graded to the level of the blue top hubs. Smooth rolling puts the finish on the surface. The completion of pad 1 required 5 construction days. On pad 2, an attempt is made to grade the area using the Case 450 bulldozer without automatic controls. 2 days are spent hauling and placing fill. However, it soon becomes evident that this small machine is incapable of leveling the fill as it is deposited by the scraper. The manually operated controls are too coarse to permit fine adjustments of the blade position. The blade frequently dips too low, which tends to stall the machine. The same instructor operator who completed pad 1 handles the bulldozer on this pad, but even his acknowledged competence is unequal to the task. The cut boss also has problems in laying down the fill on the uneven surface. An additional unsuccessful day is spent in attempting to level the fill. As a final effort, the cut boss directs the scraper to rearrange some of the material, but this also fails. Then the project on pad 2 is abandoned. On pad 3, the same Case 450 bulldozer is used, but it will be equipped with the automatic controls. The laser transmitter is a commercially available device powered by a 12-volt automobile battery. It emits a rotating light beam that establishes a reference plane for automatic control of the bulldozer blade elevation. The CEL-developed angle sensor controls the blade tilt. The construction of pad 3 begins in exactly the same way as pads 1 and 2, with scrapers laying down the fill. A major difference is the use of the laser survey rod rather than conventional surveying and staking methods. The receiver on this rod detects the laser reference plane and emits a high, low, or on-grade signal. It enables the cut boss to determine very quickly the elevation at any point on the pad and to direct the scrapers more efficiently as he builds the required slope. Now the kit of automatic controls has been installed on the bulldozer, and it is ready to attempt the same task that proved to be a failure on pad 2. It should be noted that the complete kit can be mounted on the bulldozer in the field without drilling, tapping, or welding. When the laser transmitter is adjusted for cutting to the desired grade, the emitted light beam is picked up by the receiver on the bulldozer, thus establishing control. The receiver, which is also commercially available, will remain locked on the light beam. The transmitter and receiver can exercise control over an area more than 2,000 feet in diameter. The results are quite different on pad 3. Here, the blade of the Case 450 cuts smoothly, evenly, and to the specified grade, without the need for surveying or the setting of grade stakes or blue top hubs. The operator merely has to steer the machine and control the throttle. Once the operator has set the blade elevation and angle, the fact that the blade travels automatically on grade in front of the machine produces an important result. After the bulldozer has traveled its own length in the cut, it is on grade for the rest of that pass. There is only slight adjustment of blade elevation and tilt angle by the controls as the machine proceeds. The CB operator of the bulldozer was trained in less than an hour to use the automatic controls and perform close tolerance cuts. Less experienced operators can learn to operate the machine just as readily, and exacting work can be done in daylight or in darkness. Compared to the effort expended on pad 2 or even on pad 1, this task is accomplished both easily and effectively. The smooth functioning of the automatic controls can be observed on this pass. The bulldozer blade is making only minor adjustments in tilt and elevation as it proceeds. The tilt control system uses the gravity force vector as a reference to maintain the blade tilt automatically. If the automatic control should fail for any reason, the machine can be returned to manual operation. However, the electronic components are easily changeable, and they permit field maintenance by replacement rather than repair. When grading is completed, the track marks left by the bulldozer are smoothed over by the roller. With the automatic controls and in spite of the small size of the Case 450, the construction and grading of pad 3 was completed in only 3 days. The final surface of this pad is compared to the final surface of pad 1, which was completed by the motor grader. They are found to be comparable in accuracy of surface roughness or deviation from the bottom of a 10-foot straight edge. Levels that establish the accuracy of the grade are taken with the laser survey rod. Rises or depressions in the surface that are too long to be detected by the 10-foot rule can be identified in this manner. It is determined that the surface of pad 3, constructed by the automatically controlled bulldozer, more closely conforms to the specified grade. In comparison with pad 1, pad 3 was completed in 2 less construction days, with 86% less surveying labor, 20% less labor for placing fill, and 53% less grading labor, while producing a more precise grade with equal surface smoothness. Even greater savings and quality differences would be expected if the operators had been less skilled, or if the kit had been installed on a larger bulldozer. This evaluation demonstrated clearly that the automatic blade control kit enables the bulldozer with tilt blade to accomplish high accuracy finished jobs that usually require a motor grader with a highly skilled operator, as well as the rough tasks normal to bulldozers. The development of this system will minimize the time, manpower, and equipment needed for essential earth moving in amphibious operations and logistics support ashore.
The concept of irrigation is not new. It was practiced by the earliest civilizations. In the arid regions of the world where rains are infrequent, irrigation is critical for growing crops. By pumping water from under the ground or transporting it along canals from reservoirs, water flows onto flat desert land, transforming it into profitable and highly productive food-producing land. There are many methods of irrigation in use today. The more sophisticated forms of irrigation include center pivot sprinkler, linear move sprinklers, and drip irrigation systems. In spite of large initial costs and high operating costs, these systems have grown in popularity in recent years. But the oldest and still most widely used method of irrigation is surface or flood irrigation. Since this method relies for the most part upon gravity to move the water across flat or sloping fields, it is the most energy efficient form of irrigation. To make the most efficient use of water in flood irrigation, the land must be smooth and level. For many years, farmers have leveled their land in an effort to improve irrigation efficiency and crop production. Over the years, farmers have found that flood irrigation uniformity and efficiency improved as land leveling techniques improved. Land leveling is begun by first preparing an elevation survey of the field. Conventionally, a grid of stakes is set at 30-meter intervals. For example, in a 30-hectare field, approximately 300 such stakes must be set. Using a level and a rod, a survey is made to determine the elevation at each stake. Then a field slope is selected which meets desired slope specifications or existing terrain features. Upon completion of the design, the surveyor returns to the field. This time he remarks the stakes to indicate the depths of cut to be made in an area or the amount of earth fill required. One method uses a red ribbon tied on a stake to indicate a cut, and its distance from the top of the stake determines the depth of cut. The blue ribbon indicates a fill, and its distance from the top of the stake indicates the amount of fill. After all stakes are marked, large earth-moving scrapers are used to move the soil from cut areas to fill areas. The operators visually check the grade references on each pass and make continuous passes until, in the operator's judgment, the grade is finished. The survey crew then returns and resurveys the field. Resurveying generally points out high and low areas that must be reworked. The field is regraded and checked until the field meets acceptable tolerances. Typical tolerances for land leveling jobs could be plus or minus 3 centimeters. Normally, after scrapers have finished grading, the field is smoothed or floated with a land plane to remove small irregularities left by the large equipment. Although this flooded field was conventionally level, the dry areas give an indication that high areas still exist. If enough water is used to cover the high areas, there will be an excess or wasted amount of irrigation water in the low areas of the field. Conventional leveling greatly improves the land and irrigation efficiency, but better results are now possible with laser-controlled equipment. In the mid-70s, in the southwest United States, the first laser-controlled drag scrapers were being field tested as tools to improve surface irrigation. It was proven there that precision laser leveling allowed farmers to use their precious water to better advantage, saving water, reducing pumping costs, and improving crop yields. These first laser control systems, and thousands that have been placed in service since then, were built by Laser Plane Corporation, a subsidiary of Spectra Physics. The laser plane control system consists of 4 basic components. They are the command post, which consists of the 945 laser transmitter, elevating tripod base and legs. The receiver system, which consists of an elevating mast and omnidirectional receiver. The control box. The interface kit, which includes all hydraulics, bracketry, and wiring necessary to couple the laser plane system to the tractor and scraper. This is how the system works. The laser transmitter is the heart of the system. The transmitter is a rugged waterproof unit consisting of a laser, optics, electrical, and mechanical systems. Inside the transmitter is a low-powered helium-neon gas laser tube that emits a thin beam of tail-light red laser light. The beam enters the first optics and is expanded to 2 centimeters diameter. A second lens then collimates the beam to maintain the 2-centimeter diameter. The beam then next moves into the cap, where it is optically bent perpendicular to the vertical beam. The cap is then rotated at a speed of 5 revolutions per second. The result